Hello everybody, welcome to the Greenplum meetup. And today I'm very happy to introduce Yon Lew here, who's going to be speaking about Greenplum Database performance, optimization, and tuning. I've been working with Yon for over 3 years, and he is the most proficient professional in this area. Excellent guy, and I really am looking forward to hearing the talk and all the details he has to share with everybody. So thanks for coming to the meetup, and there you go.
Hey, thanks a lot. Okay, so the first slide kind of sets up an introduction for this talk. So when I talked to Ivan, he said that one of the most searched for terms with regards to Greenplum in the Pivotal channel was for advanced tuning and optimization techniques. So this talk is pretty technical. It assumes that you're familiar with the basics of Greenplum Database. There's not going to be any review of fundamentals or basic concepts. And its intended audience is mostly technical staff, especially DBAs. Who are not new to Greenplum, but not new to databases in general. And because Greenplum is based on Postgres, if you're familiar with Postgres, you'll have a head start on the subject material. Okay, so just to start off, I want to say it's super important with Greenplum to test, right? When you work with a distributed system with many nodes, there are a lot of variables involved with running the system. And that number of variables can make performance very unpredictable. So it's absolutely essential that you test for your specific scenario rather than assuming that the guidelines I'm going to present here will work 100% of the time. Okay, so the first subject is schema design. So Greenplum is basically optimized for data warehousing. And in data warehousing, you typically have two types of tables. The first is fact tables, right? These are typically the largest tables in the database. They have a lot of columns. And we're going to usually define these as append-optimized columnar tables. The second type of table is dimension tables. And for these guys, we're going to choose a storage model that's either append-optimized row or heap storage. So why is that? So as I mentioned, fact tables are typically the largest tables in the database. They're typically very wide. You could easily have hundreds of columns in a fact table. And queries against those fact tables will often involve only a subset of those columns rather than every single column in the table. So that's basically the very definition of a columnar table storage model. And even if you don't use a traditional data warehousing model, any table with these characteristics will probably benefit from an append-optimized columnar storage model. So the thing to remember is that file storage for heap versus AO tables in the database is not identical, right? So heap and AO row tables get a single file per table. By contrast, AO column tables get one file per column, right? So if you select against an AO column table and your query only hits a subset of those columns, you're going to be able to scan only a subset of the table files, right? And that should be much faster. So there's another primary consideration when we take a look at the storage model for these tables, and that is maintenance. So when you're doing table maintenance, for instance, adding or removing a column, for heap and append-optimized row tables, what the database is actually doing on the back end is it's creating a copy of the table, and then it's going to swap the files out between the copy and the original table. So there's a couple of disadvantages to that. The first is that you're going to need twice the space available, twice the size of the table available in your database to do that swap. And there's more disadvantages. It holds a very restrictive lock on the table for a very long time. In fact, it holds the most restrictive lock that exists in Greenplum Database. And the way locking works in Greenplum is that if you lock the table with an access exclusive lock, that will prevent any type of query against the table whatsoever. You won't be able to do a count against the table. You won't be able to do a select against the table. You can't even do an explain plan, run an explain plan against the table. So the trick with AOC tables is that, again, the table is made up of a number of files, right? One file per column. So if you add or drop a column, there is no need to rewrite the entire table file for that table. It's orders of magnitude faster. And it's really going to protect users who think it's okay to change table definitions while continuing to run batch processing. Right? So you may have a situation where the user thinks, okay, I've got to add a column to this table, so I'm going to go ahead and do that, and I'm just going to shut off batch processing against it while I continue to run batch processing against the rest of the tables in the schema in another part of the database. So what's actually going to happen then is, especially for a fact table, which are, again, the largest tables in the database and often partitioned, you're going to have to copy out every single partition to a new file, right, and then swap them in. And in combination with user queries running against the database, that is a tremendous amount of load on the database. So I mean, if you try and do that with a heap or append optimized row tables, that can take a significant amount of time. So for that reason alone, in my personal philosophy, you need a very, very good reason to deviate from defining fact tables as AOC. Yeah, that said, there are some caveats to defining tables as append optimized. So append optimized tables get metadata tables, right? They have associated metadata tables. And those metadata tables need to be updated after any CRUD operation. So you insert records into an append-only table. You have to turn around after that and update the metadata tables. So that in itself is an additional load on the database. And in addition to that, you also have an issue with concurrent loads for append-optimized column tables. So the way concurrent loading works against AOC tables is that if you have 50 concurrent loads running against an AO columnar table with, say, 500 columns, what's going to happen is that each of those loads is going to create its own set of table files. So 50 loads running on a table with 500 columns is going to produce 20,000 primary segment files on a single segment host. And that assumes 500 column files times 50 loads, 8 primary segments. So, like with databases, the efficiency of any file system is going to decline as the number of files goes up, right? File systems, like databases, have to manage metadata. And if you have lots of files, you're going to be managing lots of metadata. So it's very possible in the real world for high volume loads to produce tables that are made up of literally millions of files. And of course, with that volume of files, the efficiency of your file system is going to decline very rapidly. So as workaround, you've got a couple of choices. One is to load to a work staging table with heap storage, and then insert from that into your columnar table. And another would be some kind of batch process that comes in after your ETL and rebuilds the table, either by redistributing it or by running a CTAS, a create table as select, to rebuild the table. Okay, so as I mentioned, heap tables have no issues with file multiplication from concurrent loads, right? You run 50 loads on a heap table, you still get one file per table. And again, heap tables do not have those associated metadata tables that AO tables have. So you insert to the heap table and that's it. There's no need to go out there and grab the metadata tables and update the stats for the table. So for that reason, it's ideal for heavily updated tables, right? Such as metadata, load history, load status, etc. So in summary, our recommendation is to use heap for frequently updated tables, and only use append optimized columnar for large fact type tables that are loaded infrequently. Okay, so the next subject is vacuuming in Bloat. So this should be familiar to anybody who comes from a Postgres background. So in Postgres and in Greenplum, dead rows are left in place on the table files, right? So you run a delete, and what actually happens is that a transaction ID column on each record is updated. But the dead rows themselves remain in place on the table files. So this is different from something like Oracle, for example, right, where you have an undo table space. So it's not only deletes that produce dead rows, it's also updates, right? Because an update in Greenplum and in Postgres is really just a delete and followed by an insert. So if you run a lot of updates or deletes against a table, you get lots of dead rows, right? And in Postgres and in Greenplum, we call this condition bloat. And the solution to bloat is to vacuum the table. So vacuum comes in two flavors, regular vacuum and full vacuum. So regular vacuum doesn't actually reduce the table size, right? It just scans the files and it updates the free space map to say that this extent from this address to this address is available for reuse. And that's for heap tables. So regular vacuum is actually the flavor of vacuum that we prefer for all regular maintenance. And you'll see why in the next slide. So the other flavor of vacuum is vacuum full. And this variety of vacuum actually does reduce the table size, right? And it does that by actually rewriting the files for the table to move blocks of data next to each other. But that is a very expensive operation, obviously, right? It takes out a very restrictive lock on the table. Again, it takes up the highest level lock in Greenplum Database. That lock will block any type of select. It will block any type of explain plan written against the table. And it's slower than simply recreating the table with a CTAS. The other issue is that it can result in table corruption if the database crashes, right? You cannot run vacuum inside of a transaction. So if you're running a vacuum full and somebody pulls the plug on the server and the database goes down, you could easily end up with corrupted table files on the back end. So for that reason, the recommendation is not to run vacuum full against any user table, right? It's simply cheaper and faster to create another table, a copy of the table, and then swap them. And the only exception to that is for catalog bloat, right? So obviously you cannot create a copy of a catalog table and swap them. So that's really the only situation where you would use a vacuum full. So the other thing that vacuum does, which is essential to the proper functioning of the database, is address transaction ID wraparound. Right, so Greenplum and Postgres both manage MVCC by saving a transaction ID to each record. Right, so everybody knows what MVCC is, right? That's how Greenplum and other databases manage, like SQL Server, Oracle, manage concurrency. So what happens is that every record in Greenplum has a hidden system column that records the transaction ID of the transaction that either created or deleted that record. And when you run a query against that table, what happens is the database takes a look at all the transaction IDs in the records and then compares them to the system's transaction ID. And that's the way it figures out which records are visible. So in Greenplum, like in Postgres, transaction IDs are circular, right? There's only a limited number available. In this case, about 4 billion possible values. So that's in contrast to something like Oracle, right? In Oracle, you have SCN base and SCN wrap, right, where they have two counters, and then one counter gets incremented, and so you have a tremendous number of possible transaction ID values. But Postgres and Greenplum, you're limited to 4 billion. So what that means is that every 4 billion transactions, you're going to see wraparound. And what that means is that after 4 billion transactions, right, records with transaction IDs that are older than 4 billion transactions old are going to look to the database like they're from a future transaction in the future rather than one in the past. And at that point, they're not readable, and essentially they're lost to the database. So vacuum actually addresses this by overriding the record's transaction ID with a special value, right? The so-called frozen transaction ID. But it's essential to remember that if you vacuum a table, it doesn't actually reset all the transaction IDs of all the records in that table, right? It defaults to only overriding the transaction ID for records that are older than 100 million transactions old. Oh, I got a slide out of place. Okay, so remember that Greenplum is a distributed system, right? So you have a bunch of databases that are running on the segments and a bunch of and a database that's running on the master. So the transaction count on the segments is going to be higher than the master, right? That makes sense because all the work is happening in segments. Even so, the transaction count in the segments is probably not going to be identical. Is probably not going to line up with each other, right? You could easily have a situation where you have some segments with a transaction ID of 2 billion and a bunch of other segments with a transaction ID of 2 billion and 100 million, right? So there's no guarantee that all the segments are going to share the same transaction ID. So one other thing to remember is that tables, as well as records, have their own transaction IDs, right? So normally the transaction ID of a table is actually the age of the oldest record in that table. But there's an important difference between the transaction ID of records versus the transaction ID of tables, right? A vacuum will freeze the transaction ID of a record, right? It'll override it with a special value that says this record is in the past, no matter what the transaction ID of the database is. You cannot do that with a transaction ID of a table. So the maximum transaction ID for any table in a given database is saved in the catalog, and it's used for the transaction age of the database itself. So when the cluster is looking at the age of the databases, and it's deciding whether or not it's going to continue to accept transactions, right? That's the value that it looks like. So as a safety mechanism, the database will actually stop accepting new transactions after a certain cutoff. And at some point before that, it'll start issuing warnings, right? Maybe you've seen it where you get a warning that says like database XXX must be vacuumed within 1.5 billion transactions, et cetera. So the catalog table for it's actually looking at the database catalog table to determine what the age of the database is with regards to that transaction ID cutoff. So one other thing to remember about the transaction age of tables is that you cannot freeze them, and they're there no matter what, right? So it doesn't matter if you vacuum the table and you freeze every single row in the table, right? Eventually that table is going to need to be re-vacuumed. It doesn't matter if the table is empty, right? Eventually that table is going to need to be re-vacuumed because you cannot freeze that table's transaction ID. And the database of the table transaction age can be queried so you can see how much slack you have before that cutoff. But it's important to remember that you need to do that on the segments rather than the master, right? I mentioned previously that the transaction ID on the segments is much higher than on the master because the segments are where all the work is occurring. So you need to use something like the gp_dist_random function, which is a function that reads from the catalog tables on the segments, or connecting to the segments in utility mode, et cetera. Okay, moving right along. So the next subject is SQL tuning. So the basics still apply, right? SQL tuning is the same for pretty much any database you got out there. For example, right, you always want to cut down the result set in your query as quickly as possible. You want to touch disk as little as possible, right? Especially with full table scans. And you want to limit the number of times the database goes back to the same table and rescans it. So you have to be careful of CTEs, right? So CTEs in Greenplum do not necessarily work the way they do in other databases. It's very easy to get rescans in CTEs, right? Where you do the same, you have 4 CTEs that hit the same table, and you actually end up rescanning the same table 4 times. So everyone knows what a CTE is, right? So with regards to SQL tuning for Greenplum, right? Specifically Greenplum, there is one neat trick, which is temp tables, right? So in Greenplum, creating temp tables or any table is actually really, really fast. And because it's so fast, you can use that to your advantage in a lot of situations, right? One is, I've just listed on this slide, one is to materialize for distribution. Another is materializing for aggregation, materializing to reduce the result set. Also materializing external tables in ETL, right, for complicated transforms and joins. And here again, you have to be very, very careful to actually test the query performance when you use these tricks to ensure that you're actually getting an improvement in query timings. Okay, so what do we mean by materializing for distribution? So Greenplum is a distributed system. You have data residing on a whole bunch of database nodes and they talk to each other. They have to exchange information across the interconnect. So that is a major bottleneck actually for query execution. So the fastest joins are on co-located tables, right? And by that we mean tables that share the same distribution key so that they can be joined, and when they're joined they don't actually have to exchange any data over the interconnect. So surprisingly enough, it can actually be faster to create a temp table that allows for joins on a common distribution column. In other words, that allows for co-location rather than just joining those tables across the interconnect. And the next example, the next slide is actually an example of that. So for example, we have an ETL process here, right, where we're joining two tables, A and B. And A and B share a common join column, but they're actually distributed on different keys. So in scenario 1, right, we just joined them. In scenario 2, we actually create a temp table, B temp, which is actually table B redistributed on a common on table A's distribution column, right? So now when we join A to B temp, we can actually it's actually co-located, right? It doesn't actually need to exchange data over the network, and this can actually be faster than just doing the straight join. All right, so the next one was materializing for aggregation, right? So if you have a complex query plan, it can actually be faster to, if you have a complex query that contains subqueries that aggregate over a table, it can actually be faster to materialize that to a temp table and then use that in your query, right? Depending on the query plan. So one issue is that in Greenplum, you cannot pin indexes or aggregations in memory, right? In something like Oracle, you can, we really don't care about keeping table blocks in cache in Oracle, right? What's important is to get the index and move that into cache. You don't necessarily have that option in Greenplum, but creating a temp table based on an aggregation is one strategy for getting around that. So I also mentioned materializing to reduce the result set. You can do that for a complex query where you don't think the planner is selecting the most selective result set out of the box. Finally, there is materializing external tables, right? So external tables are not reading from database files. They're reading an external source like a flat file or something. And if you're running complex queries against external tables as part of your ETL process, you can often see a increase in performance by materializing those external tables as temp tables and then doing your transforms or your joins against them. And one last thing about temp tables is that a lot of places you'll see that they analyze the temp table automatically. That is not necessarily helpful, right? If you're doing something just like an insert select from a staging table to a user table and they have the same set of columns, that operation is not going to benefit from taking stats on the temp table. Okay, so the next subject is memory. So in Greenplum, there's a session level variable called statement memory, which we use to control memory allocation for queries. So there's a great temptation to set that to a very large value across the board. So the problem is that larger values of statement mem should only be used for queries that actually need it, right? So Greenplum actually reserves memory for the query based on the statement memory. It pre-allocates it, which is why sometimes you can run an explain, right, and get a query plan and it'll run out of memory. So for small, fast queries, setting statement mem too high can actually decrease performance. And one example of that is actually analyze, right? So this is counterintuitive, right? Most people think I'm analyzing a big table. The table has hundreds of millions or billions of rows. It's gigabytes or terabytes large. I should give it a lot of memory. But if you actually look at what's happening under the covers, it's made up of a bunch of smaller queries that hit the catalog and then sample the table that's being analyzed. So this is actually an example of exactly that. I don't know if you can read this or not. So this is a database session where I'm just analyzing the PG attribute catalog table. Right? So you can see I check the size. I set the statement mem to 1 gigabyte. I run the analyze. It takes about 3 seconds. I change the statement mem back to 125 megabytes. I run the analyze. It comes back in less than a second. And just to prove that's not caching, I set the statement mem back to 1 gigabyte and do it again. You can see it jumps up to 3 seconds. So this behavior is true even when you set the cluster memory policy to equal-free. And I should also mention that it's being addressed in Greenplum 5.0. Okay, so the other area is AO tables. So remember that AO tables have associated metadata tables, and they need to be updated after any CRUD operation. They need to be read for any select operation. So if you set your statement mem to 1 gig, right, you're setting it to 1 gig not only for the write or the update to the AO table, you're also setting it to 1 gig for all the queries that run against the metadata tables. So frequent snapshots, for example, saved to a history table defined as AO or right? You're going to see a lot more out-of-memory errors compared to using an identical table defined with heap storage. So the other thing is that if you look at the type of queries that DBAs usually run, right, it's usually metadata queries. Either against the catalog or against custom custom history tables, custom metadata tables, etc. So high value and set administrative accounts to a lower value. Right, so you can change it right before you can set it to so that the scope is for a single transaction only. And so forth and so on. Okay, so the last topic I have is an actual example of troubleshooting poor query performance in the database. So this actually happened a few weeks ago. So the user called to complain about slow query performance, right? And the bad performance is limited to a single query. The system as a whole seems okay. They're not complaining running long. They're finishing on time. The problem query usually finishes in a few minutes, but so far it hasn't completed even though they started it several hours ago. The problem query runs against a table partitioned on a date key. Right? It's an ETL process that runs against that runs a daily load essentially. Runs on previous partition dates finished quickly, they didn't show a problem. And they analyze every daily partition as they load it. And in this particular analyze multiple times against the problem partition, trying to fix the problem. Okay, so the first thing we do is just run a bunch of basic checks on the system, right? So we check the load using a command center, it looks okay. We check for suspicious messages in the system logs, right? dmessage, varlog messages, varlog MCE log, that kind of stuff. And we don't see anything that indicates any problems at the hardware, file system, or OS level. We check for CPU. We check for blocking or queuing inside the database, right, to make sure that responsible for the long runtime. That looks okay. And then finally, we check query processes hosts, right? So that is just using GPSSH to connect to all of the query, all of the segments, and checking to make sure that there isn't one segment that's holding up the entire load, the entire query. So since that looks okay, what we're going to do next is we grab a process at random on one of the segment hosts, and we actually just run strace-p on it, right? And strace is just an operating system utility that dumps what the process is doing out to the terminal. So I thought that I had actually the output from strace, but I didn't, so my word for it that what we saw was that there's lots of polling and waiting. And then it does a little bit of disk I/O, and then there's lots of polling and waiting, and it does a little bit of disk I/O. So if you see a pattern like that, that is a primary indication of latency due to network, right? If it's disk I/O, you can usually see something in the system logs, something like XFS messages or process more than 120 seconds. We're not seeing any of that, right? We're just seeing a lot of latency and a lot of polling. Okay, so I mentioned before this is a partition table, and the user told us that the ETL process on previous days ran fine. So what we can do is actually go back and get a plan for the current which has the problem versus prior days that ran okay, right? And the first thing we see is that the bad explain plan is doing a broadcast, and the good explain plan is doing a redistribute, right? So it's actually doing a hash join, and it's broadcasting one of these tables instead of redistributing them. So I mentioned that network is actually a huge factor in query performance. And understanding what the query is doing with regards to network is crucial to actually tuning queries and debugging them. Right, so broadcast means what? That means that every segment gets a complete version of the table, right? So the database is going to lift up the table, and it's going to send it out to every segment, and every segment is going to get its own copy. Redistribute means that only the subset of rows that each segment requires is going to be sent out across the interconnect. So obviously, if you have a situation where a very large table is being broadcast, and that is going to be a significant performance impediment. Okay, so now we've identified the problem, right? So that definitely network is the issue. So how do we fix it? So one of the ways is trying to tweak the database parameters, right, to encourage or discourage broadcasts. So the parameter that we primarily use for that is called GP segments for planner. So this is used by the legacy planner, not by Orca. And it basically tells the optimizer how many segments are defined in the cluster. So higher values would tend to discourage broadcasts, lower values would tend to encourage broadcasts. And it can be set at the session level, like most of these database parameters. So we tried that, and unfortunately didn't work. So what else do we have available? Well, there's always reanalyze, right? So the user has already tried to analyze this partition multiple times, and it didn't actually help. But we can try and increase the stats target and rerun analyze against a bigger chunk of the data, a bigger sample of the data, and hope that the improved statistics allow the optimizer to generate a better plan, right? So what's happened here? What's happened here is that it's loaded, day after day goes by, it loads up the data for that day, everything's fine, and then you get to the problem date. The profile for the data for that date has changed, right? And it's changed in some fashion that the optimizer thinks that a broadcast is better than a redistribute. So hopefully, if we reanalyze with a higher stats target, what will actually happen is that the optimizer will be able to produce a better plan. We didn't actually try that. What we did do actually is SQL trickery. Right, so if you work for any amount of time with databases, you have a whole bunch of these SQL tricks in your toolbox, right? Influence the planner in one direction or the other. So I mean, it doesn't matter if you've worked with Greenplum versus Oracle or DB2 or whatever, right? So these tricks are actually from DB2. So I work with a very senior DB2. These tricks are straight from his DB2 toolbox, and we apply them. We try them out in Greenplum, and they actually work. So what we're going to do here with this trick is we're going to try and fake out the optimizer. Right? We're going to try and make it think that the results from a join are more selective than they actually are. So the original query is just select star from table A, table B, on column A equals column B. Right? So the trick is to put that in a coalesce statement, right? So now we're going to select from table A to table B on coalesce column A equals coalesce column B. So that actually does nothing, right? But it fakes out the planner into thinking that the result set is more selective than it is. So that's the reduced data set. What if you want to do the opposite? Well, in this case, it's selecting against a partition table, right? And it's doing partition elimination. And the way it's doing that is specifying a partition date of July the 1st of 2017. So what happens if you tell it, well, give me everything where the partition date is July the 1st of 2017, and the partition date is not equal to July the 2nd of 2017, right? I mean, that second clause is obviously useless. But what actually happens is that it pushes that second partition into the query plan. And when that happens, the database says, aha, now I have a bigger result set. I cannot broadcast that because it's too much data. So instead, I'm going to redistribute, which is the correct behavior. And this actually fixed the problem and allowed that query to run. OK, and so that's it. So I just want to mention something about the company I work for, zData. So we have a significant amount of experience with Greenplum Database. And we offer a variety of services, from managed services, health checks on existing systems to make everything looks OK, expansion for when you want to increase the size of your Greenplum plant, tuning and optimization, remote DBA services, professional services, and most importantly, training and knowledge transfer, right? Because to get the most out of the system, you definitely need to have some familiarity with it. OK, questions?
So on the statement memory, you said you would give the real user, you'd give high statement memory.
Yeah.
So how much statement memory would you give it at some point? When is the point of no return?
So I mean, it depends on the size. How's that? What?
Can you repeat the question?
Oh, yeah, sure. So the question is, how do you know what value to set statement mem to? Right? So for administrative users, you're going to set very small, right? Because you're querying metadata. But the actual users are going to be hitting user tables. So the question is, how do you know what value to set statement mem to for those guys? And that depends on the volume of the data that they're operating with, right? If they have very large tables that are gigabytes, that are gigs big, or that have hundreds of millions or billions of rows, you probably want to give them gigs of statement mem. The other thing is that the users can set their own values for statement mem, right? So if they know, and they're the ones that are going to be most familiar with their own data. So if they know that they're running a query against a smaller table, they can easily set statement mem to a smaller value for the duration of their session or for the duration of a single transaction. That's probably the best, the most optimal solution, right? Let the users handle it, right? Because they're the ones that are most familiar with their own data. Any other questions?
Do you ever do data sorting to optimize storage or anything else?
So you can, yeah. So if you don't want to do, so are you talking about clustering, like an index organized table?
Do you ever sort the data to get it to compress better? Or?
So I mean, there is something called an index optimized table, right? You can cluster tables around an index. So the entire idea is that if you insert with a sort, you push adjacent values next to each other on disk, right? So when you scan the block, if you're doing a range, you're saying show me everything where x is between 5 and 7. If you've sorted the data in your insert, you'll actually touch fewer blocks on disk, right, if you have sorted on the insert. So you can certainly do that, absolutely. Was that your question? Okay. Anything else? Oh, yeah.
So you talked temporary tables being a better choice than CTEs. Even if the data is small, do you still feel that temp tables are a better choice than CTEs?
Sorry, what was that?
Even on small data, do you think temp table is better than CT?
No, absolutely not. Right? It depends on the nature of the query. It depends on the size of the tables that you're querying, and it depends on the nature of the query that you're running. So I mean, again, right? Like I said, you have to test, right? And it's going to be dependent on a lot of variables, right? So you have to test.
So again, let me just repeat my question. I mean, do you feel that even if when the data is small, not in terms of megabytes, you feel that even still, then the CTE, your statement holds true that temp tables are better than CTEs?
So the problem with CTEs, in some other systems, if you run a CTE, it will cache the results, right? And then subsequent steps in the query plan can access those cached values, right? So it doesn't look like we get that kind of performance actually with the Greenplum optimizer yet, right? So it's very common to have a query where you define 4 CTEs against the same table. And you will see the query runtime scale linearly, right? 3 CTEs, it'll run 3 times as long as a CTE against a single table, against a single CTE. 5 CTEs, it'll run 5 times as long, right? So it certainly looks to us like it's rescanning the table over and over again. If you create a temp table, right, you get around that issue.
Give the example of where you created a temp table with the same distribution of the table you're joining with.
Yeah.
Are there scenarios where you want to use random distribution and not distribute by a specific field? What types of tables would that be?
So I mean, typically we use random distribution where we just don't have a good choice of physical keys to ensure uniform distribution across the cluster. But the drawback is that if you query a table with random distribution, the memory usage is typically much higher, right? So you have the same table, one defined with a distribution column, one defined randomly, and you run the same query against both those tables, you run out of memory on the second table, and you will not run out of memory on the first, right? So there is a disadvantage to using random distribution from what we've seen. Any more questions? Yep.
You mentioned earlier in one of your slides, the table can have millions of files.
Yeah.
Do you have any recommendations on tracking the growth?
So at the client I'm at now, we actually have 2 processes for managing that. So one is a snapshot process that runs in the middle of the night, and it just collects metadata on the file system. And the mechanism it uses for that is external table. And the external table literally just runs an ls command on each segment, and then pipes the output through grep and cat, and then stores the data in a history table. So we have that. We also have a script that you can give a table ID to, and it will run out to the segments, and it will check the number of files for that table, basically using SSH and an ls command. So there really isn't a mechanism for checking that inside the database right now, but you can certainly define your own processes, your own scripts to handle that.
I know there's a lot of users partitioning data by some type of date range. Is there any best practices, whether that should be a daily thing or monthly thing, a yearly range, just the type of query that they're using? Or?
Yeah, absolutely. I would say it's absolutely dependent on the data and on the user. So that's it? Okay, thanks a lot.
Thanks, Yon.
Oh, sure.
Question online? Okay.
Yeah.
Says, no, so question from the user is, we can change the optimizer settings at the database and session level. Is it going to be the same with Greenplum 5? I heard that it comes as a default on.
You have to answer that. I'm not sure.
You can still change, the answer is, and I'll just get on your mic, sorry, I don't know if you heard. The question was, can you still change the optimizer between the old and the new optimizer in Greenplum 5?
You have to answer that.
And the answer is that, yes, you can still change it. The default will be the new optimizer, but the old optimizer is still available. And so you can pick and choose. And I think some of the items that you mentioned, like sub-selects and some of these other things, there are specific improvements in the Greenplum 5 optimizer which will provide benefit, and so that we can then focus on the other issues. So.
Yeah, the testing we've done has shown like a 2 to 3 times improvement in query performance between 5.0 and 4.
Cool.
All right, hey, thanks a lot.
Thanks.